Welcome to the QEM Heroes webinar series. My name's Christine Wood, and I serve as the Assistant Program Director for the Heroes Fellowship Program at QEM. For more than 30 years, QEM has been a national catalyst for STEM education transformation and research capacity building. Currently, the QEM network serves nearly 900 colleges and universities and reaches more than 8,000 individuals nationwide. This webinar is part of the QEM Heroes Initiative. The Heroes program brings together experienced researchers who've worked in federal agencies to lend their expertise and support to the STEM research and education communities. Our fellows are here to provide tools and tips for navigating the funding landscape, developing STEM programs and partnerships, and improving talent retention in in-demand fields. Our goal is to build sustainable ecosystems for STEM research and education at colleges and universities across the country, not just at those with large funding portfolios. We hope this series promotes engagement with our Heroes Fellows and provides valuable resources to our participants. A note that during the webinar, you can use the Q&A tool to ask questions of the panelists. The panelists and moderators will monitor and answer questions during the webinar as time allows. Once this presentation is over, we'll moderate a discussion and give attendees the opportunity to raise their hands and ask questions live. I am happy to introduce our presenter today for this very special webinar. Dr. Yulia Gorova is a geochemist by training with a PhD from Caltech, specializing in earth and planetary sciences. She previously served as a scientist at the Smithsonian National Museum of Natural History and as a scientist and technologist at NASA's Jet Propulsion Laboratory. So without further ado, I am going to turn the floor over to Yulia.
Good morning, good afternoon, everybody, wherever you are. Thank you so much for coming. I am excited to give this webinar. This is something that I built specifically for this presentation. I've been working on Mars missions for almost 15 years, but never had an opportunity to share my experience with working with students, with getting funded myself, for getting funding for my research or for group research. And this is a brand new presentation where I put everything that I could think of together and hope you will find it useful. So what we're going to talk about today, I split it in 5 parts. They're not very big, but they will cover from academic, the Mars story and Mars exploration, to what the Mars gives us through robotic exploration and through Mars missions, where the money is for research for Mars. How can you get into the game from scratch, from zero, how to establish your research program at your institution. That's the number 4. And the concrete next steps, like what should you do if you decide to do so, and resources that are needed to achieve that. All right, number 1, the Mars story. So why this matters? Why this planet that is the only planet in solar system inhabited by only robots, and the hottest, that's cold and dry, and why it's such a hot topic? There are 4 big fundamental questions, some of them partly answered, but all of them are open. One is it has a watery past. We know for sure that Mars had water. The most recent rover Perseverance Mars 2020 mission landed specifically in a big delta. It's a river delta that opens up in a crater. So it's exploring that place that was a lake with a river that was going into it. The life question is there. Different robotic missions found organic molecules and methane and chemistry that is amenable to the life. All of that was detected. So the question of past Martian life is definitely scientifically open. It's a roadmap to humans. Every robotic mission paves the way for eventual crew missions, mapping hazards, resources, everything. So there is a lot of talk about Mars exploration, human Mars exploration, but this is the fleet of robots that crawled and crawling right now on the surface of Mars. This is what actually enables human missions. And of course, it's lab for Earth science as well. Mars preserves over 4 billion-year-old rock records that is completely erased on Earth by plate tectonics. So it's a time machine for planetary science. I meant to have this slide busy. What I wanted to show is that we have 6 decades of Mars exploration. There are many missions, and at first there were more failed missions than successful ones. In fact, in the 70s or after, like in the 80s, Mars was called the space graveyard because there were so many metal things that were crushed into it. And it started, successful missions still were started in the 60s, like Mariner 4 and 6 and 7. They didn't land, and these were flybys. They flew through the atmosphere or through the upper atmosphere and imaged surface of Mars in a close proximity. In the 70s, orbiters and landers appeared. So first lander actually, well, first number of landers were crashed by Soviets, but first a successful soft lander was Mars 3 by USSR in 1971. It lived only for like few seconds, I think, or maybe like up to a minute, and transmitted half of one image, very badly corrupted, but it landed. And then there was Viking 1 and 2, NASA missions in 75, orbiter and lander. First long-term surface operations, hugely successful. We learned about atmosphere of Mars. We measured composition of the atmosphere of Mars. We finally linked group of meteorites that we didn't know where came from to Mars. So the Martian meteorites, now we know that they are Martian because of Viking mission in the 70s. The 80s was a dead period for Mars rovers, and then 90s came Mars Global Surveyor. High resolution mapping, we are still using that mapping, the topographic maps from Mars Global Surveyor, which is 30 years old. We still use those maps. Pathfinder and Sojourner, twin rovers, two landers about size a little bit bigger than the microwave, first successful Mars rovers. 2000s, Mars Odyssey, still flying. 25 years later, it's still flying, it's still transmitting data, from the rovers that are on the surface. European Union sent the Mars Express. It's a first Mars mission from Europe. Spirit and Opportunity, also 2 rovers, 6 and 14 years respectively. Both of them were expected to work only for 6 months, and they worked 6 and 14 years. MRO, Mars Reconnaissance Orbiter, that's the main data transmitter right now from any rover on the surface of Mars to relay the data to Earth. And it provided high definition imaging, high res. I'll show you a couple of images later on. High resolution from the height of 150 miles, it's from 150 to 200 miles above the ground. You can see an object the size of a pizza box. Phoenix mission, lander, confirmed water, ice on polar soil. It wasn't very long-lived, but it did its job. It confirmed water. Curiosity rover, still crawling on the surface, studying the Gale crater habitability. First orbiter from India was launched in 2013. MAVEN, another orbiter, atmospheric escape. InSight, that's the geophysics. First seismometer on Mars also didn't work too long, but did transmit seismic data from Mars. And then we have two international other international missions, HOPE from Arab Emirates and Taiwan one from China. And finally, my personal favorite and the most modern and the most recent NASA rover, Perseverance, that's the Mars 2020 mission. I worked on it for over 10 years, from design to tests and build and operation on the surface of Mars and science team operation and decision making. I'm really grateful to have that time.
Yulia, we have a question related to your previous slide. Why were the 1980s so quiet? Or maybe a better way to ask is when and why were political leaders uninterested in Mars?
I think that is an excellent question, but I think that was a dead time, sort of like break of the Cold War. Much of the lunar exploration and Mars as well was part of the space race with Soviets. And 80s, that's when Soviet Union collapsed. So I think part of it was that. Maybe there are other reasons, but that's what kind of comes to mind. And then the next missions were more science driven than race driven. Right, I'll move on. So a couple of landmark missions. Actually, I kind of talked on the previous slides. I'm not going to spend too much time about that. Most of them are NASA, except for Mars Express and Taiwan 1. And Odyssey, MRO, Perseverance, Global Surveyor, Mars Express, Curiosity, and Taiwan, they're all active missions. So they're happening right now. What does those missions bring? So this is it's a cartoon. It's not a real rover, but this is a Perseverance rover. It's Mars 2020 mission. And what is listed here is only cameras. This rover has 7 scientific instruments, and 6 of them has their own cameras. So we have 7 science cameras. Can you see my pointer here? Can you? Okay, perfect. So we have 7 science cameras. We have which are 2 over here on the mast, 3 on the arm, on the robotic arm, this big one. 1 here, that's the weather station, weather station, and I think 1 in the back. Then we have engineering cameras. Nav cams, navigation cameras in front to see where we are going, has cams in the back to see what is behind or if we are biking up. And actually there are front has cams and the rear has cams. They're kind of lower than nav cam. They're looking right at the wheels and on the ground, and navigation camera looking ahead to see where the rover is going. Then Ingenuity helicopter that was attached to the belly of the rover at first and then dropped and took 72 flights. It's still mind-blowing. This is a technology demonstration, a little mission to see if we can fly a little helicopter on another planet in a very, very thin atmosphere. And it was supposed to make 3 flights. People were hoping it will make 3 flights, and it made 72. And in fact, for second half of its life, it flew ahead of Perseverance and scouted the ground and scouted the path where to go and scouted. I would send some images to the scientists so they could choose where to send the rover next. So that was hugely successful. technology demonstration. It also had two cameras. And then EDL and LVS. EDL is an entry, descent, and landing. This is if you saw the videos from NASA during the landing, this is the cameras that actually showed the parachute and how the sky crane detached from the capsule and pretty much the entire landing process. And LVC is a one little camera that did a great deal. It looked on the ground during descent, and it's sort of like was that not Van Moore, the self-driving cars. So it's kind of like that. It sent a picture to the computer on board of Perseverance of the ground. The computer processed that picture and fine-tuned where to land. So engineers using this camera and using this technology, engineers were able to land the rover within 40 meters of the point that was basically planned for. That's incredible precision for going to another planet. So all these cameras produce data. It produced images of various quality and different with a different purpose. Oh, I included this one. This is a Perseverance self-portrait. Remember that robotic arm in front of it? So it has a couple of mass spectrometers. It has a drill, and it has cameras where it can kind of like stretch and take a selfie of itself. But it's not one image. This image is stitched from about, I think, 60 plus images. So it's a mosaic that was stitched together to produce this kind of image. And on the end of that arm, I will talk about this. Okay, so this arm, so there are a couple of mass spectrometers that you can come very close within millimeters to the rock surface or regolith surface and to take spectra, to make chemical analysis and of course imaging. But there's also a drill. That what actually separates Perseverance from previous missions. This rover collects and already collected samples. It's collected cores and drilled into the rock, and actually have an engineering model of the sample tubes for you to show. It's a little bit of a show and tell. For those who doesn't see me, I'm holding a tube about maybe 15 centimeters in length and about uh, just under 1 centimeter inner diameter. So this kind of tube is inserted inside of the drill bit. So when the drill drills the rock, the rock core is collected directly into this tube. And then this tube is carried by the same arm and put like right here. This is a carousel. You see the round thing here. It inserted inside the rover, and there's a little small arm, also robotic arm, but the small one inside that hermetically seals this sample. So Perseverance collected almost 30 samples like that. And Mars sample return mission was supposed to bring them back. But as of now, the Congress did not fund the Mars sample return mission or cut the funding. So right now it's on hold, but we do have meticulously selected and collected pristine samples of Mars, of Martian surface in the belly of Perseverance right now. Right, so this is our self-portrait, and I'm just going to show you a few pictures of quality of imaging that Perseverance sends. This is a Mastcam Z camera, NASA JPL Caltech, but it is mostly Arizona State University baby. Beautiful, beautiful camera that makes both spectral data and imaging like that. So you can see the landscape far with like like 2 or 3 maybe ranges on the background, and you can see this rocks very close by. It takes a lot to take this kind of images because you have to focus, the focal distance changes here, right? So you have to, and again, it's a mosaic, so it consists of probably few dozen or a couple of dozen of separate images that were stitched together. Since Mastcam-Z has two cameras, it actually produces stereo images as well, which are awesome. This is a close-up, and other than mosaic, you can zoom in with highest resolution to see the texture of the rocks and actually see if it's it can be a dune, old dune with like a little bit of a lineation or just broken up by cratering. And geologists can read a lot from textures like that. Another instrument, science instrument on board is SuperCam. It's also NASA JPL, Los Alamos National Laboratory, and the French team put this wonderful instrument that zips a laser into the rock and takes a spectra of emitted, basically wavelengths, to determine a chemical composition. So we have chemical composition in spots like this. This is a close-up context, the rock that is analyzed, and this is a super camera, close-up camera. For scale, this is 2 centimeters here. So we have chemical data. This is actually a sample inside this tube. So once we collect the sample, there is another camera inside the rover, inside the belly, that takes this step images because we don't know exactly how big the core is. So it takes this number of images until some of them, at least some of the frames, are in focus. But you can see like really nice textures and white specks. It's actually sulfates, which is very exciting for from astrobiological perspective, and definitely indicates water, past water. So this kind of images. This is a NavCam, navigation camera, bad resolution because we don't need a high resolution. It's not a science camera, but apparently it catches things like this. This is the twister video taken by NavCam. And atmospheric scientists can learn about how the twisters on Mars travel, and then we can actually map their tracks and learn about atmosphere and dynamics, like temperature dynamics on Mars. Stepping away a little bit from Perseverance or from rovers, this is the image from MRO. So this one is from about maybe 180 miles high in the sky. And you can see Curiosity rover over here first. And then it moved here, and we actually can see the tracks left by Curiosity from this height. So it kind of gives you an idea of how good or how high resolution is. And formal resolution is about 25 centimeters per pixel. So the good news is that NASA mandates that all planetary mission data becomes publicly available, usually within 6 months of collection. And that means that decades of high-resolution imagery, spectral data, chemical data, topographic maps, atmospheric readings, temperatures, all of that is sitting in a free online archive or archives, a number of them. You can get orbital images, chemistry, atmospheric data, 3D topography. I'm kind of repeating myself, but this is a really big point. Not many people actually know outside of the planetary scientists know that that data is completely open and anybody can use it, can download it, can download raw images and use it. And I put here a slide. You will have an access to the slide deck Christian promised me. So if you're interested, you will be able to access all those resources from the presentation. I put a list of main depositories for the Mars data. And I'm not going to go in details, but it's PDS is the main one, planetary data system, and it's a master archive. It's both raw data and also processed by the science teams, so you can actually get results like chemical spectrum. Not everybody can actually read them, but labeled, annotated, processed, corrected, and so forth. They're there. HiRise, that's the high resolution image browser, beautiful resource. And I wanted, again, my baby, I wanted to show you the Mars 2020 resource. This is the marsnasa.gov. I'm going to click on it. Excuse me. And this is a site, Mars Perseverance raw images. So these images are same day or next day or whenever the MRO, the excuse me, orbiter sends the data back to Earth, these images appear here right away. And you can see there are, 500 million files here, and 63 new images today. And you can search from by date on Earth or Sol, which is a Martian day. They're counted from the landing date for the spacecraft. And you can also search by type of cameras, like what you want to see. So this is actually a piece of rover, which is always engineers want to see if everything is okay, if there's not too much dust or something like this, and they look at the wheels as well. And then science images are more of, okay, so this is a landscape. It's an atmospheric, actually. Looking at the horizon is the atmospheric measurements. Again, this is the robotic arm sitting very close to the surface. This is how high resolution images are taken and spectral data, chemical analysis are taken. So you can browse and you can download any of them at your will. There's a description and there is a download button. They're about 5 megabyte, I think, each. So that's the resource for Perseverance. All right, so this is all of it is a free access. So what can you do with that? So I was thinking that maybe some of you want to start a research project on Mars exploration, but where do you start? You do start with something that is clearly available. If you don't have funding, you don't have money, you don't have a active research, you start with available data. And that's the depository that I showed you in the previous slide. And here I just threw in a few ideas that are easily done, can be done, and they're definitely publishable by an undergraduate student. And of course, it's not a limiting list, just few ideas. You can do crater morphology analysis. It's always needed because we date surface of Mars by density and depth of the craters. You can do recurrent slope linear RSL mapping. This is basically short-lived water marks or traces of short-lived water on the surface of Mars. Dust devil and wind pattern tracking. You can do it visually from MRO. MEDA is an instrument on Perseverance that takes images, also measures temperature, surface temperature right at the ground, just a little bit higher from the ground and about 5 meters from the ground. So it's a gradient of temperatures, and also it has a microphone that can listen to winds and things like that. All that data is available. And of course, mineral mapping with CRISM, traverse analysis, even machine learning on high resolution images. There's like 73 excuse me, 1,000 landmark labeled data set. So a computer science student can do an AI project on this kind of data and train a classifier or validate that data. Tools. So next step after you download the data or look at the data. Okay, let's back up. Sorry about this. So this is my visual of a pathway to a beginning or starting the project. You choose a mission, pick a mission, whether it's a curiosity, perseverance, MRO, anything. You go to PDS or any of those depositories that I showed you. Download data, images, spectra, topography, chemistry, play with it. There's a lot to learn. There is a lot to observe. If you have experience in some planetary geology, you don't have to have experience in planetary geology. If you're a geologist like me, I started as a geologist, you can read it. You can understand the topography, you can understand the features, you can understand the morphology, and think about questions to ask. You can analyze the data locally, and this is the tools. These are common tools, but I list them here because so it would be easy to find what kind of data can be processed with what tools easily. And then submit your results. In science, we have one deliverable, for science research, we need published papers. If you want to establish a research program, small, big, you have to publish. So start small, get free data, find a small project with a student, and publish it. That's sort of like a first step that you do. Then you can think about how to expand your project, where to find funding. I put here 4 probably the most relevant funding sources. And the good news that smaller colleges and underserved institutions are explicitly targeted by some of those programs. And you can be yeah, so four of the sources is the mission instrument team COI roles. This is the hardest one to get to. You have to grow into it. You have to have network. You have to have already. You have to be established in the field already to approach PIs as a part of the bigger proposal. To have your part on it as a COI, as a co-investigator. But it's done. It's done all the time. The PI provides a cover, and you, as with your project, with your ideas, you provide your expertise. Funding for that is variable. EPS core and BRAP capacity grants. These are specifically for underserved states and MSIs. So it's for building infrastructure. And I put approximate amounts as of past year. I don't know if it changed this year, but this is what sort of the bulk that is given for this kind of grants. Research grants, NASA ROSAS and SFAG, these are standard research awards, peer-reviewed, typically 3-year grants. I lived about 12 years on ROSAS researches. I funded my own research and my lab and salary. I did need to have PI at the institution that I was at, who was very happy to provide their name with me writing a proposal. And this is something to do for like a postdoc or a graduate student. You can just write your own proposal. Any PI will be happy when somebody comes with a ready proposal, for a grant proposal, and say, hey, can you sort of be on it? And I will do the work. Data analysis grants. This is the lowest barrier. No hardware, no facilities needed, just expertise and data skills. They're smaller, but they're more accessible. So also something probably to start in the beginning of your research, building your research program. NASA ROSES has four different sources for funding for Mars exploration. The main one, big one, is solar system workings. It's pretty much everything in the kitchen sink in that program. Studies of planetary processes, atmospheres, geology, and so forth. What I want to draw your attention to is MDAP, because it is, I believe, most relevant. It's explicitly for analyzing existing Mars mission data. So that free data that we have. And I'm looking to the left because I'm watching the time. I have about 5 minutes. I want to leave some time for questions. So this Mars data analysis program is specifically for analysis of already existing data. Planetary data archiving, also good one, that's funded to help researchers create, improve, or upgrade planetary data archives. PDS is a big archive, but it's not very user-friendly. So clearly, a specialist in that field are needed. And open source tools as well. So you can get funded to build or improve open source planetary data tools. It's also related to C19. So MDAP is really the best first grant. You don't need anything other than questions to answer, existing public data, and your expertise. Any US researcher at any institution can apply, including community colleges. You don't have to have, definitely not R1 level institutions, anybody can. It's about 80 to 200K per year for 2-3 years. Strictly like undergraduate data analysis project is on the lower side, but it is, I think they have about 40% funding rate. So it's a really high probability of actually funding that, getting funding in this MDAP realm. What kind of science? Pretty much everything. Can students be paid? Yes, students are essential for this kind of grants. Both graduate and undergraduate can be funded as research assistants, and it is explicitly encouraged by this project, by this program. NSF, I'm not as familiar with NSF. I'm a NASA person, but the AAG, I know that AAG Astronomy and Astrophysics Research Grant funds planetary surfaces, atmospheres, geology of solar system bodies, including, of course, Mars. What I wanted to point out to you is RUI, that's the research at undergraduate institutions. If you are in an undergraduate institution or a community college, you apply for NSF AIG grant just like everybody else. It also peer reviewed, it goes through the same panel. But if you're marked as or classified as RUI or apply for RUI, you are given a special consideration because we do want undergraduates and we want fresh bodies in the field and undergraduates to join and start their own projects in a few years. So RUI within AAG at NSF. NASA EPSCoR established program to stimulate competitive research. This is specifically if your institution which is in an underfunded or underrepresented state. It's annual. It's fairly healthy, 750K per 3 years. But you do have to check whether your state qualifies. Many states in the South and Plains, of course, do, and also Puerto Rico, Guam do qualify. And there's also rapid response research, fast-tracked or urgent or emerging research topics. I'm not sure how Mars research fits into that, other than, hey, I finally saw a Martian. That's the life. I need to get finding. I don't know, but it is another funding opportunity within this program that is fairly low-hanging fruit, relatively, of course. MUDEP, lowest barrier, Minority University Research and Education Project. If you fall under this category, if your institution falls under that category, apply. the M plan, it's a small one, a small grant. Your student or you work directly with other researchers for 6 months. You get experience, you get connections, you probably will get publications. It's only 6 months, but it kind of jumpstarts a research program. And then MUREP, institutional research, that's the biggest award. This is highly competitive. It's to basically build another related research center at your institutions. It is possible, but it would have to be really established research program already at the institution. And on annual omnibus, of course, multiple awards released as appendices throughout the year. So keep an eye on MUREP, NASA's MUREP program, because appendices come up and change regularly. So just check what's going on, and maybe there is an opportunity that you can apply for. All right, I think it's the last one, space grant. All 52 space grant consortia, or all 52 states have space grant consortium. And each of them distributes subgrants, fellowships, internships, conference travel, and so forth. Again, they're not very big, but if you want to start a project, you need to start somewhere, you need to go to conferences, you need to build your network, and you need to apply for this kind of grants to support your students to attract them and to actually build your program up. Other programs include NSF PAR, which is a partnership. Planetary Society is a private funding. There are two small but very prestigious grants. Every student and early researcher should apply for them. It's a Shoemaker, Jen Shoemaker grants. NEO and Jen Shoemaker grants. They are small, but this is something that your student can put on a resume, and it pretty much will set them up, not set them up, but definitely will help to advance their career, having that behind the belt. SETI Institute, some source of funding. I'm not quite familiar, but I know that they do fund Mars research. And state science academies. Many states have state science academies, and not that many researchers know that they exist and that they provide funding, space-related funding. So they're overlooked. Check them out, contact them in your state, and be proactive with these small bricks that from which you can actually start building a program. All right, you don't have to do it alone. Partner with an R1 university. They bring infrastructure, you bring students, and bring ideas. International collaboration. Anybody except for China right now, all of them have open data and sometimes, open data. And a letter of collaboration from international partner strengthens any NASA proposal. And I've been to many panels and I've seen that. If you have a partner, international partner, your proposal kind of like jumps up in a pile. Join the NASA Center collaboration. Also, almost any NASA center has or had some JPL undergone severe cuts. So is Goddard Flight Center and JC a little less, but there are big force reductions right now. But I think there are still collaborative programs to some level exist. And consider integrating it as your team. This is your advantage. You have people there to dig through data, to mine through images, and actually find and solve some of the questions that you can formulate with them. Right, citizen science, I think we talked about that. This is volunteering when you can actually play for that, but also a really good way to find collaborators. Conferences, Lunar and Planetary Science Conference, the biggest one, Woodlands, Texas, every March. I went there first time in '95. It had about 200 abstracts. Now it's over 2,000. So the conference grew significantly. Pretty much everybody who works in planetary science and on Mars will be at that conference. If you cannot go, they actually have travel grants for students. They're competitive, but it is possible to apply and get support from them. Division of Planetary Sciences, Astrobiology Science Conference, and of course, American Geophysical Union Fall Meeting in San Francisco, if you like, 10,000 people in one place. Right, that's it. This is pretty much my last slide. We have our data. We need to play with it. We need to process it, and we need to find funding. And I kind of build it as a timeline as phase one, first year, get your bearings. Phase two, build your credibility. By that time, you should be publishing or at least submitting a paper. And then phase three, once that is successful, the phase three is scale up. That's when you applied for a bigger, like a really research project, not just sustaining project, but a research grants. So that's the action plan. For 3 to 4 years, and your program will be built. So this is it. Mars is waiting. Data is free. The questions are open. And this is me on Mars Yard, a Jet Propulsion Lab with a full-scale Perseverance rover on the back. And in the front, that's the helicopter. It kind of looks big. It's much smaller. It's maybe like this size, maybe. But these are life size models, and they are testing and actions that Perseverance is still doing on the surface of Mars and collecting that data that maybe some of you will be analyzing, or your students. Right? And I'll conclude with our three QR codes with event pages, Heroes webpage, and webinar feedback form. Please give a feedback. I personally would really like to know whether you found this presentation useful. I want to see what my personal next one, which is next month, is going to be, or how to tailor it for audience. And any suggestions or criticisms are always welcome. And I think I'll open up for questions. That's perfect. I have almost 15 minutes. And I'll open it for questions.
We do have a couple of questions. The first one is, are there any funding opportunities available for forensic research?
On Mars? I don't know. I do not know, but I have to think about it, because you probably maybe something tied to the human hazards on Mars. Not directly. So let me say this. I'm not aware of any funding opportunities for forensic science that is directly linked to Mars. But there might be wordings and solicitations that may appeal to a specific type of research that you're doing, the person who asked the question. So look it up, look at the roses, look at all the resources that I gave, and maybe there's something that may reflect the need for the forensic science on Mars.
Okay. Our next question is, your slide that recommended research projects for undergrads included one for computer science and AI students. Do you have any specific AI tools and processes you might recommend for research on Mars, or recent papers on methodology using AI that students might use?
This is a really good question. I'm not an AI person. I put that suggestion just from the, maybe flip it back very quick. Sorry about the, the labeling of the images is kind of a mindless job, but then you need to train AI or train the classifier. And that's just sort of my this entire slide is the ideas that came to my mind as a pilot study, like what you can try to do. But one thing that this question reminded me about is that Perseverance actually used AI last year to to drive itself. Perseverance has a escapes me right now, but AutoNav, yeah, auto navigation. This is a system that it uses pretty much almost since the landing, which means that the rover scientists can give a point where the rover have to go, and then a rover goes, the has cams and nav cams take images, computer process them, and then tells them, okay, so we need to bypass this rock, for example, or we can go over it because it's small enough, and so forth. But last year, the engineers actually came up with an AI model that completely calculated the route for the perseverance through like obstacles and everything. And I'm not an AI person, so I cannot explain that, but I know that there is a technology that even appearing right now, it's not embedded in the rovers. In the rover, but apparently engineers came up with an AI model that planned Perseverance's route to a certain point. So it's like more than NAVCAM. It's actually it's self-driving car, completely self-driving car.
All
So
right. So our next question is, was there a reason why the U.S. was more intrigued by Mars exploration than any other nation?
uh, well, actually, US was more intrigued in space exploration in general, not just Mars and Moon, of course. Moon was a big thing during the space race. Mars is the next planet. US has been a leader in space research. So I cannot say that they are specifically more interested in Mars than other planets, but there are just more missions from US because it has been a leader in space science and space exploration until pretty much recently, which right now the landscape is changing.
Okay.
And the US had been to the moon, never got to Venice, or a little bit, very close, but Russians beat us to that. No Mercury yet, but definitely many missions to outer planets, to Saturn, to Jupiter, to interstellar, like already past solar system. So there are many missions. So Mars is just something that I chose to focus for this presentation, and it is close to my heart. So that here it is.
Okay. Our next question, from an educational point of view, how realistic is it to build a simplified Mars habitat in a university lab so undergraduate students can perform microbial survival tests under the Mars-like conditions?
There's an interesting, well, realistically, it's probably very difficult. There is a experiment, Biosphere 2. If somebody had been to Arizona, just north of Tucson, it calls a Biosphere 2 because Biosphere 1 is our Earth. And that's exactly what they did. They put this habitat and sealed a bunch of people in there for 2 years, I think. And they were growing food and they were completely, or they thought they were completely isolated. But the experiment actually failed for different reasons. Mostly, I think, because oxygen was seeping through concrete walls, some like really engineering thing. So I think it's actually fairly difficult to really reproduce Mars conditions, especially in this sort of a university type setting. This is Biosphere 2 is large. It's still open. You can go and see it sort of tour as a museum. But it might be very difficult to do it, especially if you also want to reduce pressure and or depressurize it.
So I want to clarify on this question because I think the person is really asking, can you create a Mars habitat in a lab space so that they can do microbial survival tests?
Oh, okay. All right. I was thinking like on a much bigger scale. Um, yeah, and actually that had been done. I think if I think a little bit, I probably even come up with the research groups that are trying to do that. But all you need to um, low pressure, low temperature environment, controlled very thin atmosphere, so you can all put gas there and can do a very specific gas mixture. You just need sort of a double door access for manipulation if you need that. So yeah, yeah, I think you can do that.
Okay. And then our final question, I would like to check the action plan for phase one. What should I register for free?
This is a space a state space grant consortium and inspires the two things that I recommend to register right away. Space grant pretty much gives you it sends you email if there are some grants available or solicitations or needs. It's also a way to connect with people who also work on space research in your state. And Inspires is NASA solicitation grant website where all the solicitations in one place. And you need to register actually both your institution and yourself separately as a researcher. And then you will be able to see past and current funded proposals, new solicitations, old solicitations, and all the submissions and reviews are done through that website. So if you want to keep track of that, register.
And we have someone who has raised their hand with 2 minutes left. I am going to enable Francis Carter Johnson to speak and ask a question. Francis, you're on.
Good afternoon. Great presentation. Dr. Yulia, I don't want to get your last name wrong. Can you all hear me? Yes?
Mhm.
Okay, great.
Yes.
So, Yulia, I wanted to check, kind of give a follow-up to the first question. Are there any funding opportunities available for forensic research using Mars data? From my experience advising researchers to do research on different topics. Forensic research is like a different methodology. And as long as they can use forensic research to answer a question of interest to NASA or to NSF, whoever they're applying to, I would think that it can be used as a methodology to answer a relevant question using Mars data about Mars exploration. Do you agree?
That's excellent point, Francis.
Okay. Thank you. That's all I wanted to just do a follow-up. So thank you.
We are at time. This was a wonderful presentation. Yulia, can you go to the last slide again?
Oop, sorry.
Perfect. Now, just as a reminder, these QR codes are available to you. You can check out our upcoming events. We have a great webinar tomorrow on conducting workshops and trainings. The Heroes webpage lists all of our Research Heroes Fellows, and the webinar feedback form is available for you to evaluate today's presentation. Thank you so much for coming today, and we will see you at a future webinar. Thank you.
Thank you so much for coming.